Hi, I'm Mark Barsamian. In this video, I'll be discussing valid and invalid arguments. This content is from section 2.3 of the book. First thing I want to talk about is what are called arguments and argument forms. First, the definition of argument. An argument is, well, here's the symbol for an argument. It's this strange looking thing here. What is this? Well, each of these lines, each of these expressions, that one, all the way down to even this one, all of those things are statements. Now, what does this symbol mean? Well, what it means is this big symbol, which you realize is a great big conditional statement. It reads this way: if premise 1 and premise 2 and premise 3 and so on all the way down to premise k, if all of those, then conclusion. So an argument is simply a different way of abbreviating and presenting a great big conditional statement. So an argument is a statement. For example, here is an argument. It's one of these things presented in this strange way, this stack of sentences, and the bottom sentence has this little 3 dots. So what does this mean? It means one great big conditional sentence. I'll write that sentence down. So this means if the capital of Ohio is Columbus, and 5 is greater than 7, and kangaroos are marsupials, then the moon is made of green cheese. That's what it means. Now, the way that this would be read would just simply be this. The capital of Ohio is Columbus, 5 is greater than 7, kangaroos are marsupials, therefore the moon is made of green cheese. So those 3 little dots are spoken therefore. But what it really means is this big conditional statement. Now here's a question. Is that conditional statement a true conditional statement? Well, let's figure that out. Notice that this is true, but this is false, and this is true. So this great big AND statement, true and false and true, is false. Conclusion is also false. But remember, this is an if-then statement. This is true. Remember that false arrow false is true. So this weird argument is actually a true statement. Now I want to introduce the definition of argument form. It's the same as argument, but the premises and conclusion are all statement forms, not statements. So the symbol is exactly the same. The only difference is that all of those items on that list are statement forms. Previous definition, all of the things on that list were statements. So what does it mean? Well, it means in symbols the exact same thing. And it's the meaning in words is the same thing. If premise 1 is true and premise 2 and ... all the way to premise k, then conclusion. So it's just an argument form is simply a different way of abbreviating a great big conditional statement form. So an argument form is a statement form. It becomes true or false when you actually substitute in actual sentences for the statement variables. So let's do an example of some argument forms and their corresponding statement forms. So I have 4 examples here, and we'll simply write down the corresponding statement form. If the quantity if P then Q and P then Q. Now that's kind of awkward to read aloud. It's actually maybe clearer if we just translate into a statement form written in symbols. Now in that presentation, I don't need any more parentheses because the last thing done according to the order of operations is this arrow. But it can't hurt for clarity to put all the hypotheses in some parentheses. So there is the statement form that corresponds to this argument form. It means the exact same thing. What about this next one? There it is written in symbols. Let's write it in words. So if P then Q, and not Q, then not P. Let's do the third one. There it is in symbols and in words, and finally the last one. Okay, so you get the idea that an argument form is just simply a statement form in disguise. Now I want to talk about valid and invalid argument forms. First of all, a valid argument form. Here's what defines a valid argument form. No matter what statements are substituted in for the statement variables and the premises, if the premises are all true, then the conclusion is also true. That's the definition of a valid argument form. Now, what's an invalid argument form? An invalid argument form is one for which it's possible to substitute statements in for the statement variables in the premises in a way that the resulting premises are all true, and yet the conclusion is false. And that's the definition of an invalid argument form. So practically, how do we test an argument form to determine whether it's valid? Well, the answer to that is you make a truth table. So, for example, let's use truth tables to determine if the argument forms from the previous example are valid argument forms or invalid argument forms. So here we need to make a truth table for this. We need to have columns for all of the statement variables. So we need to have a P and a Q. And then the only thing else that's mentioned in this argument form is this conditional argument form, P arrow Q. So we make a column for that. Now we populate the rows, or we populate the columns for the variables first, starting with the rightmost variable, going true, false, and then moving over one row and alternating true, false half as fast. And then we populate this column by doing if P then Q. Now remember how that goes. If P then Q is only false in the one situation where P is true, Q is false. Okay, so there's our data. Now what are we supposed to do with this? We're supposed to investigate all the situations where both of the premises are true. There are the premises, so we have to find the rows where both of those are true. So let's make a little asterisk for the premises. So if this is premise 1, we put a little asterisk to denote that it's a premise, and this is a premise. So we could put a little asterisk by those columns. So that column gets an asterisk, and this column gets an asterisk. So we're looking for the rows where both of those columns are true. Here's one row where both the premises are true, and that's the only row where both premises are true. So what we have to do is we have to check to see if the conclusion is true in that row. And it is true. So the conclusion is true in all the rows where all the premises are true. Maybe turn that around. In all the rows where all the premises are true, the conclusion is true. In all the rows where all the premises are true, the conclusion is true. These are called critical rows. So our truth table has one critical row. So our conclusion from this is that this argument form is valid. Let's go to the next one. How about this argument form? Test to see if it's valid or invalid. Well, we need to make a truth table that has columns for all of the rows of this argument. So first of all, we have the variables p, q. Looks like we're going to need not p, and we're also going to need not q. So let's put those in as columns. And then let's put in a row for p arrow q. So we populate the statement variables. We populate the statement variables first. Then we can populate the not p column by negating this. And we populate the not q column by negating the q column, of course. Now we have to compute this column, p arrow q. Well, we did that before. We do if p then q. There's the p q data. So there's the if p then q column. Now we have to identify our premises and label the premise columns. And we have to identify the critical rows. The critical rows are the rows where both of the premises are true. That's this row here. Now, what's the conclusion? The conclusion is this. So we have to look at the conclusion and see if it's true or false. And we see that the conclusion is true. So again, in every critical row, the conclusion is true. So we conclude that it is a valid argument form. Now let's go to example 2c. Let's consider our third argument form and see if it's valid. See if it's a valid argument form. So we make columns for the statement variables and for any other statement forms that show up in the argument form. So we have a statement variable p and another one that's q. And we have the statement form if p then q. Now we populate this table. We populate the q column first, then the p column, and then the if p then q column. Now we identify the premises and label the columns that contain the premises. And then we identify the critical rows, the rows where both premises are true. And notice, now we have to identify the conclusion, and we have to look in the critical rows and see if the conclusion is always true. And we see that in this row, the conclusion is true, but in this row, the conclusion is false. So there is a critical row where the conclusion is false. So this is an invalid argument form. That's the end of that example. Let's go on to the next one. Example 2D is to investigate this argument form to see if it's valid or invalid. So we have the same statement variables, p, q, and we're going to need not p, not q, and we're going to need if p, then q. Now we've actually already filled in this table. I'm just going to quickly populate it. There's the table. We identify the columns that contain premises and the column that contains the conclusion. And we identify the critical rows, the rows where both the premises are true. So here's a critical row, both premises are true. Here's another critical row where both premises are true. Now let's look and see what's going on with the conclusion in those rows. Well, here is a cell where the conclusion is true in the critical row, but here is a cell where the conclusion is false in the critical row. Since there is a critical row where the conclusion is false, we conclude that this is an invalid argument form. That's the end of that example. Now, so far we've only seen two valid argument forms and two invalid argument forms. It turns out that they're famous and they're given names. The first one was this one. It was valid, and it's called modus ponens. The second argument form, this one, was also valid, and it's called modus tollens. The third argument form was invalid, and this gets a name. It's called the converse error. And the fourth argument form that we studied was also invalid, and that argument form gets a name that's called the inverse error. Let's check the validity of more complicated argument forms. You have a problem like this in your homework. Use a truth table to determine if this argument form is valid or invalid. Oh geez, well, so we need columns for all three statement variables, so P, Q, R. And it looks like we're also going to need a column for negation of Q, so I'm going to put that here. I didn't make this table big enough. And we're going to need a column for this, P or Q. We're going to need a column for this, if P then not Q. And we're going to need a column for this, if P then R. So let's populate this table. First of all, I populate the statement variables. Then I take the negation of Q, so I have to negate this column to get this one. Then I have to do P or Q, so I have to do the OR of these two columns. Then I have to do if P, then not Q. Notice that I filled out these last four very quickly because anytime the hypothesis is false, the conditional statement is true, regardless of what's going on with the conclusion. Finally, I compute if P, then R. First of all, I'm going to go quickly. Notice that anytime the hypothesis is false, the conclusion, the conditional statement will be true. And then we just need to consider the cases where the hypothesis is true. Now we identify the premises and the columns that have premises in them. And then we identify the conclusion and the column that has the conclusion in it. We identify the critical rows, the ones where all the premises are true. So there are three critical rows. Now we look in those critical rows to see if the conclusion is true in those critical rows. And we see that there is a row, a critical row, where the conclusion is false. So this is an invalid argument form. That's the end of that example. You can see that to verify that an argument form is valid or invalid with a truth table is a very time-consuming process. Now, we've talked about invalid and valid argument forms. Now I want to talk about an invalid argument. An argument is called valid if its associated argument form is a valid argument form. And an argument is called invalid if its associated argument form is an invalid argument form. That may seem kind of strange. Let's look at some examples. Here's an argument. If Cleveland is in Athens County, then Cleveland is in Ohio. Cleveland is in Ohio, therefore Cleveland is in Athens County. So first of all, let's write this argument in symbols. Let's call that P. Let's call that Q. So using those symbols, here is the form. We recognize that form. That's an invalid form. That's the converse error. So it's an invalid argument form, so it's an invalid argument. That is, this is an invalid argument form, and so this is an invalid argument. Now, there's an observation to make about this. In this argument, the hypotheses are true. If Cleveland is in Athens County, then Cleveland is in Ohio. Well, that's true. And it's also true that Cleveland is in Ohio. So the hypotheses are true. And look at the conclusion, though. The conclusion is false. So let's go through that again. If Cleveland is in Athens County, then Cleveland would be in Ohio. That's true. And it's also true that Cleveland is in Ohio. So the hypotheses are true. All right, so that first example of an argument is an invalid argument because its associated argument form is an invalid argument form. Now let's look at this argument. If Nelsonville is in Athens County, then Nelsonville is in Ohio. Nelsonville is in Ohio, therefore Nelsonville is in Athens County. Well, let's use symbols to denote this argument. Let's call that P. Let's call this Q. So this form would be that form. Now look, that's an invalid form. That's the converse error again. Now, why did I do another argument that's so similar to the last one? It turns out it's invalid again because the associated argument form is invalid. That argument is invalid. Why is this interesting? Well, because in this argument, the hypotheses are true and the conclusion is true. So even though, so Nelsonville is in Athens County. That's a true statement. So you might wonder, well, so what's wrong with this argument? Why is it called invalid if the hypotheses are true and the conclusion is true? Nelsonville is in Athens County. Well, the reason that this argument is invalid is because its form is invalid. If it were a good argument, then the argument would always work. And we've already seen that this argument doesn't work, in fact. Let's go back to the previous example. The exact same kind of argument led us to this dorky conclusion that Cleveland was in Athens County, and it's clearly not. So this argument is called an invalid argument because it's an invalid form. Let's go to this third example. If Nelsonville is in Athens County, then Nelsonville is in Ohio. Nelsonville is in Athens County, therefore Nelsonville is in Ohio. Let's use symbols to abbreviate this. So let's call that P. Let's call this Q. There's the argument form. We realize that's a valid argument form. That's modus ponens. Since that associated argument form is valid, we say that the argument is valid. Notice in this argument, the argument's valid. It has a true hypothesis, true conclusion. Okay, let's go on to another example. Example D. Consider this argument. If Cleveland is in Athens County, then Cleveland is in Ohio. Cleveland is in Athens County, therefore Cleveland is in Ohio. So what's the abbreviation for this? What's the logical form for this argument? There's the logical form of the argument, and that's a valid form. That's modus ponens again. Since that's a valid argument form, we say that the associated argument is a valid argument. But look, there's something very interesting here. This statement is a false statement. So we have a valid argument with a false premise and a true conclusion. So that's kind of weird. It's a valid argument, but it has a false hypothesis and a true conclusion. One last argument. If Pittsburgh is in Athens County, then Pittsburgh is in Ohio. Pittsburgh is in Athens County, therefore Pittsburgh is in Ohio. So let's abbreviate this in symbols to make a corresponding argument form. Well, look, there's the modus ponens, valid argument form again. So since the argument form is valid, we say that the argument is valid. But look, there's all sorts of weird stuff going on here. This is false. To say that Pittsburgh is in Athens County is false. And to say that Pittsburgh is in Ohio is also false. So we have a valid argument with false hypothesis and false conclusion. So that's weird. So some observations about valid and invalid arguments. It's possible to have an invalid argument with true hypotheses and true conclusions. We saw that in example 4b. It's possible to have a valid argument with false hypotheses and a true conclusion. 4d was that type. It's possible to have a valid argument with false hypotheses and a false conclusion. So surprising things can happen in arguments, regardless of whether they're called valid arguments or invalid arguments. Of course, the weird things that can happen in arguments are all things that we want to avoid. So it's helpful to be able to recognize the weird things in order to better avoid them. But we're most interested in learning how to build valid arguments with true hypotheses. Because note that if an argument is valid and has true hypotheses, that will automatically have a true conclusion. Example 4c was this type. This one about Nelsonville. If Nelsonville is in Athens County, then Nelsonville is in Ohio. Nelsonville is in Athens County, therefore Nelsonville is in Ohio. So that's an example of a valid argument, and it has true hypotheses, and it has a true conclusion. So since those are the kinds of arguments that we're most interested in, we want to focus on those and give them a name. And here's the name. An argument is called sound if it's a valid argument and it has true hypotheses. And again, if it's valid and it has true hypotheses, then the conclusion is going to be true as well. So our goal for this first part of the course is to learn how to build sound arguments. Now, so far we've only encountered two valid argument forms, modus ponens, modus tollens. They get special names because they occur very frequently. There are other valid argument forms that also occur frequently and are also given names. They're presented in this table in the book, and they're called rules of inference. So the table just titles them as valid argument forms. But the thing is, there are lots of valid argument forms. The ones that are famous make it into this table, and they're the ones that we refer to as rules of inference. So what do we do with these rules of inference? Well, we use them to build and justify valid argument forms. Remember, 2 pages ago, we stated our goal as to learn how to build sound arguments. That means that we want to build arguments that are valid and that have true hypotheses. And that means that we want to build arguments that have valid argument forms and have true hypotheses. So now we'll focus on the first part of that goal, learning how to build valid argument forms. It turns out that a good way to learn how to build valid argument forms is to build them up from other known valid argument forms. That's what these are. These are the known valid argument forms. At each step of the building process, one states which known valid argument form is being used, and the process is called deducing the conclusion from the premises. So here's the process given a nice green box. So the method of using the rules of inference to deduce a conclusion from a given premise, or from given premises. So the preparation is you start by writing down all the premises, each on a line with a number in front and the premise and the word premise afterwards. And then you draw a dotted line after the last premise. And then you add a numbered line that has a number in front and has a conclusion written that makes a new valid argument form. And then on that line you have a justification in the form of a citation of one of the rules of inference. And you continue adding numbered lines until the desired conclusion is reached. That desired conclusion will be the last line. Draw a dotted line above the last line. So that's all very vague, but I want to have that written down so we can look back at it again. Knowing how to use the rules of inference in this manner is an acquired skill. You have to have in mind what steps are needed and how those steps can be justified using the known valid argument forms, the rules of inference. One way to start to understand this process is to take a given argument form that's known to be valid and to fill in intermediate conclusions with justifications. So we're going to fill in intermediate conclusions that will make it clear why the given argument form is valid. That's what we'll do in our last example. You have a similar exercise in the homework. So here's our final example. It's about deducing a conclusion from premises. So the argument form shown at the right is known to be a valid argument form. Now the goal is to verify that it's a valid argument form. Now, verifying it using a truth table would be terrible because there are 6 statement variables. That means the truth table would need to be 64 rows. That would be an incredible amount of work, and it would not make you any smarter. It would just be you cranking out those trues and falses, hoping you don't make a mistake. So you wouldn't learn anything from that, and nobody would want to read it. Instead, a far smarter way to verify the validity would be to do the following. Use the rules of inference to deduce the conclusion from the premises. So that is, use this procedure to deduce the conclusion from the premises. So here we go. We're going to follow the procedure. First thing is we write down the premises numbered with the label that they are premises. So there we've done the first step in that procedure. We wrote down all the premises, each on a line with a number in front, wrote down the premise, and actually wrote the word premise afterwards. Now we have to do this. Add a numbered line with that has a number on it and a conclusion written on that line that makes a new valid argument form, and we have to justify it. What do I mean by that? Well, look, think about this. These last 2 lines here. This line says U is true or W is true. This line says, well, W is not true. So look, if we know that U is true or W is true, but then somebody tells us, well, W is not true, that means that U is going to have to be the one that's true. But we're supposed to justify this using our rules of inference. Let's go up and look at those. Look at this rule here. If I know that P is true or Q is true, but then I find out that actually Q is not true, then that tells us that P is going to have to be the one that's true. That's what's called the rule of elimination, and it's elimination A. And notice that it requires that you know two things. You have to know that P is true or Q is true. And then you have to also know that Q is not true, and then you can make the conclusion. So I'm going to use that rule to add a line to our argument form. So notice I added a number in front, and then I added this this statement form that's just U. And what I've built now is this thing is a slightly larger argument form, and it's a valid argument form. If I were to test this with, the premises are all true, and if I were to test this with a truth table, I'd find out that this is a valid argument form. And look at my citation. I gave the name of the rule of inference that I used. It was that elimination A. And I cited the rows in our current argument form where this stuff was happening. All right, now let's look what we've got here. We have the fact that U is known to be true. And oh, look, up here we have a line that says, if U is true, then P is false. So we can combine those to say that therefore P is false. That's our 7th line. Now, how do we justify that? What is the rule of inference that lets us know that if I know that U is true, and I know that if U is true, then P is false, then I can say that P is false? Well, let's go back up and look at our rules of inference. The rule that we used is this: modus ponens. If P, then Q, P is true, therefore Q is true. So I have to say the lines in our current argument form where those things happen. So there's a new line where I added a statement form, and I've created a slightly larger valid argument form, and I've given a justification. The justification mentioned the name of the rule of inference and mentioned the rows that it was applied to. Okay, let's go on. I know that P is not true. Oh, but look, we have a line way up here that says, if I know that P is not true, then I know that all this junk is also true. So we can use those two things combined to add another line, line 8. Therefore, R and not S. So how did we apply that? Well, we used modus ponens again. And we should say, how did we use it? Well, we used it on lines 1 and 7. If you take these two circled lines and you apply modus ponens to them, you get this as the result. Let's go back up and review our procedure again. So we've been doing this. We've been adding numbered lines to our argument form. Each time we have a number in front, we have a conclusion that is a statement form that makes a new valid argument form, and we have a justification for that line. Let's keep going because we're not done. Now let's see, where can we go from here? We know that R is true and the negation of S is true. But wait a second, where are we hoping to get to? We're hoping to get to this. We're hoping to end with the statement that R is true. We're almost there. We know that R is true and S is false. So if both of those things are true, then we can certainly say that R is true. So, if your car is a Chevrolet and it's red, then you can certainly say that your car is a Chevrolet. You can just say that one part of it by itself. Well, so that's going to be our statement 9. But wait a minute, how do we justify that by the rules of inference? Let's go back up and look at those. Look at this rule, specialization. Specialization says if you know that P is true and Q is true, then you can say therefore P is true. using the specialization rule. Now it's specialization rule A. So we're going to use that rule. We applied specialization A to rule 8, and we got this new statement here, a new statement form. Well, wait a minute. That's where we wanted to end. Again, that was the last statement that was actually given to us in this argument form. We were told this was a valid argument form. We wanted to verify it. Well, so let's go back down. Here is where we add a dotted line above the last line. So you realize that all of this stuff was part of the given argument form that we were told in advance was going to be valid. Our job was to demonstrate that it's valid, and so we did that by inserting these additional lines. Each one of them is justified by these statements, by these rules of inference, and we end up with this giant thing, which is a giant valid argument form. We know it's valid because at every step of the way we built something a little bit bigger by using a rule of inference, so we knew that the thing that we built each time was a new valid argument form, and we ended up with this valid argument form that we wanted, that has the conclusion that we wanted at the end. So that's this method of using the rules of inference to deduce a conclusion from given premises. So that's the end of that example, and that's the end of the video. Thank you.